Okay, let's pick up where we left off yesterday. We had taken our derivative, got the equation to one fraction, had found our critical point to be the cube root of 80. I'm going to go ahead and leave it in that form, although if we were on a calculator part of the test, you could go ahead and use your calculator, find that value. I'm going to use the cube root of 80 and just think of some numbers that I know that are bigger and smaller than that. And again, if I have to, I can leave them in cube root form. A number that's less than the cube root of 80 would be the cube root of 27. But that would be 3. And now I can go back and substitute 3 into my derivative. If I put 3 into the bottom, I'm going to get a positive. If I put 3 into the top, I get 3 cubed is 27 times 2 would be 54 minus 160. It's going to be a negative. So I have a negative divided by a positive. That's negative. Pick something bigger than the cube root of 80. We could use cube root of 125, which would be 5. The bottom is positive again. 5 cubed is 125 times 2 is 250 minus 160 would be positive. So I have a positive over positive, and that's positive. So this decreases and increases. Now we go back and we look at what they ask us for. We're trying to use the least amount of material, so we're looking for a minimum. We now know our minimum occurs at x equals the cube root of 80, which let's go ahead now and I'll switch that over to decimal. So if I do the cube root of 80, I get 4.308869. You want to go out a little bit farther than just 3 decimal places if you're going to use a rounded answer and have the final answer to 3 decimal places. Now the next thing that we need to do, after we've taken our derivative, we were on step 6, we have now checked the next thing we should do is check the endpoints. On this problem that doesn't make sense. We'll look at some later where endpoints would make sense and then what we're talking about. One of the endpoints would be this. That's the maximum and minimum values of x. The smallest value of x would be if x was 0. We've already talked about that would mean there wasn't a rectangle or there wasn't a box there. Then we need to make sure we answer the question, okay? Is x equals the cube root of 80 what they asked for? Well, if you go back, it says find the dimensions. So that's not what I want to know. I know what x is, but now I need to find out what h is. So x is the cube root of 80, which said was 4.309, if I round it. Then I'm going to find out what h is. Well, if you go back right immediately before you took your derivative, actually a couple steps before that, when you solve for your variable, back on step 3, you have your h in terms of your x. H is 40 over the cube root of 80 and then squared. Remember, that's 80 to the 2/3. Bottom is the root, top's the power. So now I could use my calculator to do 40 divided by 80 to the 2/3 and get that that's 2.154. So my dimensions would be 4.309 by 4.309 by 2.154. That's the answer to the question. We'll look at just a couple more of these kinds of problems so you can be familiar with the ones that are going to be on the homework. One problem that's very typical involves using a rectangle. Okay, an example would be something like this. A farmer has 100 meters of fencing to enclose a rectangular garden. What should the dimensions be? To maximize the area. And what is the area? So it's kind of a two-part question. All right, so a farmer's going to have 100 meters of fencing. He's going to enclose a rectangular garden. So let's go ahead and kind of get a picture here. I want to figure out what should my length and my width be so that I maximize the area of the garden. So step one, write an equation about the quantity they gave you. Well, they gave you 100 meters for fencing. Well, in this case, that would be the distance around the rectangle, your perimeter. So 100 would equal 2L plus 2W. Step number two, write an equation for what you want to maximize or minimize. You want to maximize the area. So area is length times width. Step number three, take the first equation and solve for a variable. In this case, it really doesn't matter which one you solve for. So I'm just going to take 100 equals 2L plus 2W. And let's just solve for L. So I would subtract 2W and then divide by 2. Now, because everything in the top is divisible by 2, let's go ahead and make that 50 minus W. Then on step number 3, the next thing that we do, remember, is to substitute that back into my formula for step 2. So then L is 50 minus W times another W. So your area would be length times width. And I know that L is 50 minus W. Step number 4, we want to get this in a form. We could take a derivative. I'd rather not do this as a UV, so let's go ahead, since it's easy enough, and distribute. 50W minus W squared. Then we can take our derivative. That's step number 5. Okay. So we take a derivative. We get A prime would be 50 minus 2W. Set that equal to 0. And now I'm going to get my critical point is 25. Now I need to show, and that was step number 6, was to find the critical point. Now I need to show that that is going to be my maximum or minimum. So then we'll go here and make the width 25. We'll pick a number less than 25, or let's say 10. If I put 10 back into the derivative, remember we're doing A prime. If I put 10 into the derivative, I'm going to get a positive number. If I pick a number bigger than 25, let's say 30, to put in, I'm going to get a negative number. So this goes up and then down. So our max is at W equals 25. So we've now verified that that's our maximum. Now, this is a good problem. We can talk about the endpoints. In this case, the endpoints won't make sense, and usually they don't. Actually, this is step number 7. Check the endpoints. What would the endpoints be for this? Well, if I took all 100 meters of fencing and I applied it to the length of this, then the maximum length I could have would be 50. Each side could be 50. But then that wouldn't make sense because that would make the width 0 and you don't have a rectangle. So that would be an endpoint, was where I would use all of that value for one of those quantities. Then the other thing I could check is, what if I had taken, let's erase this here, that fencing and made the length 0? I'm going to have what's the maximum and minimum those could be. Well, it could be that the length was 0, but then that doesn't make sense because we don't have a rectangle either. All right, so we've checked the endpoints. So nothing there to do with those. And usually the endpoints don't work on these. And then number 8, we're going to make sure we answer the question. So let's go back. The question was, what are the dimensions? What should the dimensions be? So we know one of them. We know that the width is 5. Or 25, sorry. Now let's find the length. And if we go back to where we solved for a variable, here's what the length is. The length is 50 minus W. So that would be 50 minus 25, which would make it 25. And the length would be 25. So if you look at it, in this case, then your rectangle for your garden actually needs to be a square. By the way, a rectangle is, or a square is a rectangle. It just happens to be a special one where the length and the width are the same size. So then my rectangle needs to be a square that's 25 by 25. All right, we'll look at one last problem. This one's actually going to involve a cylinder. So let's look at a cylindrical can with no top. Whether things have tops or not is really important. Must hold 42 pi cubic centimeters. What are the dimensions of the cheapest cylinder to construct? Now, just realized that we didn't answer the second part to our previous question. So let's go back just quickly. And I did not, that was a two-part question. So let's look at this. We didn't answer the part about what's the area. Okay, we did find that the dimensions were 25 by 25, but we do need to also find, we need to put units on those. Those were 25 meters. The dimensions of the square would be 25 by 25, and the area would be 25 times 25, which would be 625, and that would be square meters. So that was the last part to that problem. That was a two-part problem. Okay, now let's go back and look at our cylinder problem. So a cylindrical can, no top, is going to hold 42 pi cubic centimeters. What are the dimensions of the cheapest cylinder to construct? So let's think about a picture here. So we've got a cylinder. Doesn't have a top. And we've got to have it hold 42 pi cubic centimeters. So by looking at the units on that, I know that that's volume. If you look at your formula for volume, volume of a cylinder is pi r squared h. So we know that 42 pi has to equal pi r squared h. So that's our first step. Now, the next part's the part that's going to be a little tricky because you may not remember this formula. And I am going to show you where it comes from. To find the surface area of a cylinder is actually constructed by using two circles, if it's got a top and a bottom, and a rectangle. All right, now, this one doesn't have a top and a bottom. It only has the bottom. So it's made with one circle and a rectangle. This distance is the height, which is also that distance on the rectangle. Now, the part that's a little tricky is what is this distance, the length of the rectangle? Well, the length of the rectangle is actually that part of the cylinder. So that's the circumference, which we know to be 2 pi r. Now remember, to find surface area, so I'm going to put A for area, we find the area of all of our shapes and add it together. Well, the first shape we have is a circle, so its area is pi r squared, plus, and the second shape we have is a rectangle. But to find the area of a rectangle, we do length times width. So it'd be 2 pi r times h. So my surface area for my cylinder would be 2 pi r squared plus 2 pi r h. If I want to have the cheapest can, then I want to use the least amount of material, which would be surface area. Now, step number 3, we're going to go back to our first equation, that 42 pi equals pi r squared h, and we're going to solve for a variable. Well, by far the easiest one there to solve for would be the h. So let's divide both sides by pi r squared. Pi's cancel. So that gives me that h is equal to 42 over r squared. Number 4, step 4. Oh, wait a minute. First we have to substitute that in. So that would make my area be pi r squared plus 2 pi r times h, but we're going to put in h to be 42 over r squared. Now, step number 4, we want to simplify. So area would equal pi r squared plus, now I can take here and cancel an r here with an r there and get 84 pi, that is being over 1, over r. And now, step number 5, we're ready to take our derivative. So my derivative would be a prime equals 2 pi r minus 84 pi over r squared. And again, this was 84 pi r to the negative 1. Negative 1 comes down, makes that negative 84 pi r to the negative 2, which would be over r squared. We'll put that over 1. And let's get this to a point where we can find the critical points. So I'm going to go ahead and crisscross applesauce here. 2 pi r cubed minus 84 pi over r squared. Okay. Set the top equal to 0 because now we have a fraction. Set the denominator equal to 0. The bottom's going to be 0 if r equals 0, but that's not feasible because we couldn't have a cylinder with a radius of 0. So then we take 2 pi r cubed minus 84 pi, and we're going to solve for that equal to 0 and solve for r. So add an 84 pi, and then divide by 2 pi. So r cubed would be equal to 42, and that would make r the cube root of 42. And now we're ready to check to see if that's going to be my maximum or minimum. So we do the cube root of 42. Again, we can pick some numbers, and if we don't know how big the cube root of 42 is, pick some numbers in terms of cube roots we do know. The cube root of 8 is 2. Okay, so let's put 2 back into our derivative. Well, we can tell the bottom's always positive because it's squared. So then all I have to do is deal with the top. If I put 2 in, 2 cubed would be 8. 8 times 2 pi would be 16 pi. Minus 84 pi would be a negative. So that's negative. Pick something bigger than the cube root of 42, like the cube root of 64. The cube root of 64 would be 4. So if I put in 4, I'd have 4 cubed is 64 times 2 pi, which would be 128 pi, minus 84 pi, and that would be positive. So this decreases, then increases. And we were trying to find the cheapest, which would be a minimum, and we found that. So we now know that the radius is the cube root of 42, which if we want that in decimal, we could switch that over. And the cube root of 42 is 3.476. Then we also need to find out, because the question was what was the dimensions, so we need to find out the height. And if we go back, we have a formula for the height of our cylinder. It's right here. It's 42 over r squared. So the height is 42 over r squared, which would be 42 over the cube root of 42 squared, or 42 over 42 to the 2/3, which would also simplify to 42 to the 1/3, because we could subtract the exponents, they're the same base. 1 minus 2/3 would be a third, so I really just need the cube root of 42. And if I do the cube root of 42, we already had that, it was 3.476, which is kind of cool. It was the same thing we had for the radius. So what you want, you probably could prove this, that if you want to maximize or minimize your materials, that what you want is your cylinder to have a radius that's the same as your height, which means your cylinder is actually twice as wide as it is tall. So you want to have a wide, short cylinder, and that would construct the cheapest can. We'll also apply the same kind of concept to the pop can that I talked about, where we'll know 12 ounces. We can take, instead of 42 pi cubic centimeters, we can actually take 12 ounces and change that over to cubic centimeters using some conversions, and then figure out what size pop can you should have so that you have the minimum amount of material used, and then we'll compare that to the actual pop can construction.